Welcome to the Advanced Statistical Physics course. It's lecture 4, and the subject is Fermi Systems, mostly electron gas, at low temperatures. These are contents. First, we start, as usual, with Summation Rule, introduce Fermi energy. Then we consider completely degenerate Fermi gas, which is behavior of the system for t tending to 0 in this limit. And the third subject is almost degenerate Fermi gas, so still KBT is small with respect to relevant quantity, chemical potential of Fermi energy, but still it's finite, and we'll see effects of finite T. Next. So we start with the general formula for the number of electrons. So it is sum over Fermi distribution, and this is a Fermi distribution. So it differs from both distribution by plus sign here. Epsilon J is energy of one electron in the state J. Mu is chemical potential, which for fermions also called Fermi energy, and KBT is energy. So in our case, J also contains two components. The first component is momentum, and the second component is spin. It's projection of the spin, which runs from minus S to S, and the number of states is to S plus 1, both for fermions and bosons. It's a universal formula. However, so for fermions, S acquires value plus minus 1/2, plus minus 3/2, and so on. There is no zero here. The summation rule, we know it. So sum over all state of anything, general summation rule. This is spin factor G, spin degeneracy, it's called. V is the volume, 2 pi h cubed. It's unit volume in the phase space. An integral over all momenta, the momentum space, whatever we sum here, at this point it should be expressed as a function of momentum. In most cases, for certainty, we will set S equal 1/2, which corresponds to electrons, or for that matter for neutrons or protons. All of them are fermions with a spin 1/2, and then G is equal to. Then the summation rule becomes, the next slide. So the 4 pi and 2 from spin degeneracy give me 8, cancels anything denominator, 1 pi is gone, so pi squared, h cubed as it was. Now let us apply this rule to the total number of particles. So if I substitute here the Fermi distribution, p squared is left from the element of volume, p squared dp is the element of volume, and this coefficient is here. Also, there are fermions of two types. There are massive fermions, so non-relativistic, and they have quadratic dispersion rule. Also, there are fermions that are ultra-relativistic, or having zero mass, such as very fast electrons, neutrinos in all cases, are ultra-relativistic. And then dispersion relation is different, but here in this lecture, we'll consider specifically massive particles, non-relativistic particle, and take this selection rule. Dealing with this integral, as always, you need to take this epsilon as a new variable. So if you take epsilon as a new variable, then p is square root of 2m 1/2 epsilon, and the epsilon, if I differentiate this, is p dp, and p dp is nothing else as m d epsilon. It is the same. So d epsilon is PdP divided by m, multiply m, we get PdP. Now we will substitute this P and PdP to this equation. We'll get. So n is equal 2 to the power of 1/2. This is from square root of 2m epsilon. M to the power of 3/2 pi squared h cubed. This is what instead of p squared is dp. So this is p squared and dp together. Now the integral expressed in terms of energy. And what is it here? This coefficient is Fermi distribution expressed in terms of energy. If you look at this formula, if I remove integral, then this element of the number of particles. So it is everything except for this integral. If you integrate it over all epsilon and from n from 0 to n, you get back this expression. So they're equivalent. Now we can calculate internal energy to get thermodynamics. Because as we know, internal energy is nothing else as integral epsilon dn. So this extra epsilon in this integral brings up the power to 3/2. So this expression gives us connection to thermodynamics. Now let us consider properties of the Fermi distribution expressed in terms of energy. I repeat the formula here. So epsilon is energy, mu is chemical potential, synonymously called Fermi energy for fermions, kBt is temperature, plus 1, bring to attention, plus 1 is always for fermions. For bosons, in the previous lecture we had here minus sign, but to the end of the course you'll be studying fermions, so we will keep the plus sign. Now we consider temperature to be small enough, so the thermal energy kBt is much less than Fermi energy, which you will find shortly is purely quantum mechanical energy. Actually, we have shown this at the previous slide, and we'll be using it in what follows. So the classical energy, thermal energy kBt, much less than quantum mechanical energy that follows from Heisenberg uncertainty relation. It's due to localization of electrons caused by finite pressure, finite density. So if so, that obviously if I set epsilon is less than mu, that is numerator here is big negative quantity with respect to kBt. So this ratio is a big negative number. This exponential is exponentially small. With this exponential precision, I only leave 1 and nf is equal 1. In this case, nf is equal 1. In the opposite case, I take epsilon greater than mu, then this quantity typically is much, big numbers, much greater than kBt, so ratio is a big positive number. Exponential is exponentially large, you can neglect 1, and nf is exponentially small. Basically it's 0. And conclusion is that Fermi distribution for the degenerate gas, and the degenerate gas is this condition, is practically 1 below the Fermi level and 0 above it, the transition within interval of energies determined by classical energy, kBt, classical thermal energy. So here I show you a calculated Fermi distribution for one single valent metal, so metal where there's one valence electron per atom, and those are all alkaline metals: sodium, potassium, rubidium, and also there are monovalent transitional metal, particularly coinage metal or noble metals, which are used in plasmonics: gold, silver, and platinum. Of course, there's also a bivalent metal or two-electron metal, or 2 valence electrons per atom. Those are alkaline earth elements, which are calcium, magnesium, and strontium. And there even is a trivalent atom, there are 3 valence electrons per atom, which is aluminum. They have typically higher Fermi energy. So for monovalent atoms, Fermi energy is about 5.5 electron volt. Almost the same for all metals. So this specific value, 549, is for silver. It's experimental data for silver. We use 2 temperatures: 300 Kelvin, it's a room temperature, and then 3000 Kelvin. 3000 Kelvin is basically the highest temperature a metal can withstand. It melts above it. Though when the molten metal is still a metal in some sense, not crystals, we can talk about Fermi energy and conduction electrons. So at this point, okay, it's 2 minutes. We continue with lecture, and to remind you, at the end, when the presentation is over, we have ample time to ask questions regarding any part of this lecture. In fact, if you have of the previous lectures. Okay, next slide. Again, I repeat that if thermal energy is much smaller than the Fermi energy, such Fermi gas is conventionally called degenerate. In particular, in real metals, the electron gas is always degenerate in all the realistic range of temperatures, because Fermi energy is almost 6 electron volts. 6 electron volts is 60,000 Kelvin. And the thermal energy is 300 Kelvin. So this is a factor of 20. KBT is less than mu. So this can be safely assumed, and then it will allow us to simplify expression for thermodynamic variables and also evaluate them. I think we'll start with N. This, I repeat, the expression we obtained. So here, this is the Fermi distribution factor, the coefficient at epsilon 1/2 d epsilon. And this is 1 when epsilon is less than mu, and 0 for any practical purpose when epsilon is greater than mu. So this integration cuts at mu. And in this range, this factor can be replaced by 1. This is integral of a simple power function. 1/2, I get in 3/2 a corresponding coefficient. So this is number of particles in terms of chemical potential or Fermi energy. We can immediately resolve it with respect to mu and find Fermi energy, mu of Fermi energy, as a function of density. This is this expression. This is interesting. So what it has n over v to the power of 2/3. If it were power of 1/3, then in the denominator would be typical characteristic distance between particles, or localization radius of a particle. It gives squared. So here in the denominator is squared. We call it sometimes a squared. So h squared divided by 2m a squared. This expression known to you from quantum mechanics is that the energy due to uncertainty of momentum, because you localize particle with a certain radius given by their density, so the momentum cannot be 0. It is finite, and energy associated with this momentum gives this finite Fermi energy. And this is expression with all correct coefficients. The same can be expressed in terms of Fermi momentum. This is momentum at the Fermi surface. So for this ideal gas, to m epsilon f power of 1/2, this expression momentum through energy. And I substitute this epsilon f, I get very simple expression for Fermi momentum. If you look at it, it's a simple ratio of h over a. It is simply Heisenberg uncertainty relation. Next slide. At this point, let us evaluate numerically the Fermi energy for a typical one conduction electron per atom metal, such as silver. It's called monovalent atom. Monovalent metal, or monovalent atom, metal atom. These are relevant properties of silver, which you only need to know to calculate it. You need to know atomic mass, which is mass of silver atoms in the amount of 1 mole. And also you need to know the specific density of metal. So it is a mass of metal per 1 cubic centimeters. So if I divide density by atomic mass and multiply by Avogadro number, I get numerical density. It's very simple. Mass, the atomic mass, divided by Avogadro number is mass of single atom. And this is density divided by mass of single atom, give you a number of metal per cubic centimeter. Here. So this is density of silver metals and corresponding density of electrons. That's 1 electron per atom. And S is a Avogadro number known precisely, 6.02 10 to 23. Now we need to substitute this into equation for the Fermi energy, which is repeated here, and immediately give you energy of 8.82 10 to the minus 12 erg, or it is 5.51 electron volt. An experimental value you can find at this reference in our hyperphysics course, written by Rod Naves, a wonderful teacher, a wonderful person, now retired, is 549. So the agreement will be within a couple of percent, maybe 4%. We didn't have any adjustable parameters, so we just took everything from experiment. It's a remarkable agreement, which tells you that really electrons in the metals, real metals, are almost ideal fermions. So now let us turn to the internal energy given by equation 8. And I'm repeating this equation here. This is equation 8. As we have done for number of particles, we will cut this integral at the chemical potential because the Fermi distribution is practically 0 above it. And I will get the following expression. So with only the epsilon to the power of 3/2, the epsilon will be left. Integral runs from 0 to mu. And I take this integral, it's 3/2, will give me 5/2. 2 will go numerator, 5 to denominator, that's what we have here. And this mu, epsilon f, it is the same. Epsilon f, Fermi energy, to the power of 5/2. Now, going back and recalling that equation 10 gave us for the number of particles, and I repeat equation 10 right here. I can divide U by N. That will give us an internal energy per 1 particle. And this is understandable expression 3/5 epsilon f. It's approximately half of the Fermi energy. So all energies from 0 to Fermi energy are occupied, and the average is 3/5 epsilon Fermi, or 0.6 epsilon Fermi. A bit more than half of epsilon Fermi. Now we'll take epsilon f, which we calculated before in equation 11. This I repeated here. and substitute it in this place, and I'm getting expression for internal energy of completely degenerate electron gas. It is at zero, effectively at zero temperature. Temperature is completely neglected. It's purely quantum mechanical expression, which contains H. The particle acquire energy because they are localized by pressure. There is finite volume available to them. That causes localization and the finite momentum, which translates into energy. This is this expression for quantum mechanical energy of localization. Next slide. I repeat this expression here, equation 17. And again, mention that obviously limit of temperature equals 0. In this limit, of course, entropy is equal to 0 and U is equal to F, the Helmholtz free energy. Cv is du over dt, the constant V and N, because T is not in here, I'm getting 0. This approximation, of course, there is no thermal capacitance. It's completely degenerate gas. Nevertheless, I can calculate pressure as du over dv at a constant S and N, or F, the constant T and N, S and T, both equal to 0. Gives us following expression. Simply you remove volume, decrease power of volume by 1. So was 2/3 become minus 2/3, become minus 5/3. And 2/3 coefficient in front of it, so 3 goes this way, getting 5 instead of 10. This can be easily calculated without paper. This pressure is very important pressure. This pressure that ideal electron gas at 0 temperature exerts on walls of the container. In classical mechanics, this pressure must be 0. At 0 temperature, pressure always 0, because the only reason for having pressure is a classical motion of electrons. There is no such motion at 0 temperature. In quantum mechanics, again, there is energy localization of electrons. And when I decrease volume, this energy increases, and this causes pressure to be finite. Though finite, it very rapidly grows with density of gas. It's not the first power as the classical physics, almost second power, it's 5/3 power. While effect of this pressure in semiconductors and metals is relatively small, though not 0, you can find evidence of it, major application, when it defines almost everything, is in theory of star equilibrium, especially of neutron stars. And neutrons are fermions with spin 1/2. The star is compressed. Its final stage before collapsing to a black hole is a purely neutron star. So the force that collapses it is gravitational force, and force that counteracts it is force of pressure of those fermions. Of course, there is finite temperature, this radiative pressure, but as I remember correctly, radiative pressure is negligible with respect to the pressure of the Fermi gas, and this is the force that the only important force that counteracts the gravitational force. And if it cannot do so, then star collapses. So it is a major formula for astrophysics. So such an electron gas that has Cv equals 0 is called degenerate. This is conditional degeneracy. Classical energy kBT is much less than Fermi energy. We can substitute Fermi energy, this one, which was in equation 11, and then we get a degeneracy condition in this form. H squared over m. This is again square of distance between particles. It's in the denominator. So this all is quantum mechanical localization energy. It's much greater than kBt. This is known to us expression. And again, metals satisfy it with very high precision. So at this point I will stop. Our next subject will be almost degenerate Fermi gas. And almost means the temperature is still small, but we'll take into account in the leading approximation. So again, this is a condition that we have was given by equation 19. I repeat it here. This is conditional degeneracy, but now I will not consider extreme case. I will try to keep the leading term that contains temperature, leading non-vanishing power of T in an expansion. We need to return to the correct potential for our variables, which is mu, V, and T. And this is the current potential. And we know that for all ideal gases, Fermi or both, we have general formula. Omega is minus 2/3 U. So this is, I multiply expression for U. It was given by equation 8. And I'm getting this. So this is expression for omega for ideal Fermi gas. All correct coefficients. Now I cannot simply cut integration of Fermi energy and replace the Fermi distribution by 1 because I need to take energy into account. So now let us consider this integral, which is not trivial in this case. It has the following form. I denoted I, just this integral, and moreover I'll take general function. This integral can be calculated for any function f. So in our case, f of epsilon is epsilon 3/2, as written here. And we will be using only this f, but it's equally easier to calculate it for arbitrary f. So the approximation does not depend on form of f as long as the dependence weaker than exponential, particularly for any power. The following calculations are somewhat involved, and to tell you, many formulas that we will be using are pretty long. They're not difficult, but they're long and bulky, requires your utmost attention. It is not unusual in physics to have such computations. I took them from a textbook from Landau, you can find there. But what is important, what I would have done if I were you after lecture is over, I would have reproduced them. Try to reproduce them by heart without looking to notes. It's very important that you do it yourself. Just you do it once, you do it twice, you do different cases, and suddenly it's easy. It's only one way to learn it. Okay. To learn is to suffer through. That's my personal belief. Let's go into this. So we will be transforming the integral that I introduced at the end of the previous slide. So this integral with Fermi distribution of a function f of epsilon. And this function is any function whose growth is weaker than exponential. Maybe any power, logarithm, cosine, sine, anything like that. Anything that in the real plane with increase of epsilon grows weaker than exponential. We start with the substitution. Epsilon minus mu is equal to kBt z, or z is epsilon minus mu divided by kBt. So again, the new variable is argument of this function. It's dimensionless argument. It's a z. This d epsilon will be differentiate kBt dz. And we'll get the integral. So the argument of function, it's epsilon. Epsilon is mu plus kbtz. We have it here. This argument of exponential is z. That's also true when epsilon is equal infinity, z is equal infinity, so integral goes to infinity. But the lower limit changes because when epsilon is equal 0, z is equal minus mu divided by kbt, and it's right here. And this kbt coefficient is here. So this is simple substitution. Now, I will break this integral into two parts. From this lower value, minus mu of kbt, to 0, and then from 0 to infinity. Trivial identity. And then in the first integral, I will substitute z to minus z. So that will make the sign minus disappear, and dz will change sign, so I will change the order of limits. It will be from 0 to mu over kbt, and it changes sign over z here, so it will be mu minus kbtz, and sign of z in the exponential. The second integral is without change. Next step, I will invoke an identity. So I will multiply numerator denominator by e to the power of z. I'll get e to z plus 1. Then in numerator, I will add and subtract 1. The first part give me 1, this one. The second part give me minus 1 divided by ez, e to the z, e to z plus 1. And obviously I'm trying to get the same denominator and the second integral to have common denominator. So we will using that change the first integral only, and we will get so that what's left when I have 1 in the identity, and this is second term of the identity minus sign, and it changes sign of this exponent here. In this integral, I will again make a substitution and pronounce argument of this function, a new variable epsilon. So the dz will be minus d epsilon divided by kbt. This kbt will go away. This is this minus. From u to 0, f of epsilon d epsilon, or changing order of limits, integral from 0 to mu f of epsilon d epsilon. And interestingly enough, this integral does depend on temperature. So I is equal the first integral. Now I have the same denominator. And I would write them together, except this limit is infinity and this limit is finite. So far, up to this moment, we did all transformations exactly. There was absolutely no approximations. Now we will introduce an approximation, and it's valid with very high accuracy. This integral here converges exponentially at large z, and therefore denominator grows exponentially when z become large, and therefore the contribution to integral is exponentially small. Therefore only z on order of 1 contribute. However, if z on order of 1 contribute, then this term is relatively small with respect to this. And when z at the upper limit, z mu over kbt is very large, this condition of degeneracy, chemical potential much greater than temperature and energy units. Therefore, z never gets to this value contributing to the integral. Again, when z is large, so z is mu divided by kbt, this exponential cuts it. So it should be much below that limit. So z much smaller, z much smaller than this value, mu divided by kbt. It means that because it never gets to this value given contribution, I can replace this value by infinity for any practical purpose. Now imagine z is 1, and this ratio we know is 100 to even 1000. It never gets to this upper level. 1000 for quantity that contributes a value on order of 1, 1000 is infinity for any practical purpose. So I'll put infinity here. If I put infinity here, these two integrals become identical. I can write it with one integral. We obtained I is equal. The first integral very small, it doesn't depend on temperature. And the second integral, I have two functions. This was original function that I got from my transformations. Wrote them together because now the integrals have common upper limit infinity. The denominator is z plus 1. So it's well converges. Again, if you look that z is on order of 1, then this term is much less than mu. And this term is much less than mu, because kbtz much less than mu, z is on order of 1, because of denominator. And say this is 1000, this is on order 1, 2, 3. Of course, I can expand it over this small quantity. In Taylor series, I'll take, in fact, the lowest contributing power of z. So it will give me. This term goes without change. Here I expand. The first order will give me kbt, will be coefficient multiplied by this kbt. Give me kbt squared. The derivative of this function is z equals 0, which will be f prime of mu. And then z will be, and it's constant, doesn't depend on z. I'm taking it outside of integration. What is left of Taylor series, the first power of z, is z plus 1. And of course, I can continue this. This power will grow, derivative here will grow, and power of z here will grow. But I do not need it. This is the first term that is not 0. This leading term, and I will keep it. But if needed, I can actually write the entire series, which again I do not need. So the integral of this type can generally be expressed in terms of standard function. So if the argument here, x minus 1, is the exponent of z, then this integral is analytically exact is 1 minus 2 to the power of 1 minus x, gamma over x, where gamma is Euler's gamma function, zeta of x, zeta is Riemann's function, which we know, we already used it. In our case, exponent of z is 1, so x is equal to 2, and this term is simply 1/2. Gamma is equal to 1, and zeta of 2 is pi squared over 6. So the whole result is pi squared divided by 12. In our case, f of epsilon is epsilon to the power of 3/2. For f prime at the value of mu is 3/2 this power, mu and 1 power less, one unit less power, so 1/2. This is the derivative. And we get our leading approximation, this is leading term, depending on temperature, of I. So it contains two terms. First, does depend on temperature. Second, contains two powers of kbt and 2 power less of mu. Both have dimensionality of energy. So basically, I replace second power of mu by second power of kbt. and kbt is much less than mu. So this really small term, which is quadratic in our parameter, and parameter is the kbt divided by mu, the small parameter. Now, this integral and substitute into expression for omega that we had. So this was the coefficient, just remind you, this from equation 20, this coefficient. The rest was integral that denoted as I, just got I, and substitute I without changing anything. This is what we got at the end of the previous slide. And we only left a leading expansion term here. This was plus and so on. We left the leading term. So this basically is an approximation, but it's a very good approximation, because our parameter is about 10 to minus 3, 1000, and we have square of it is 1 million. So next term will be a million times smaller than the one that we took into account. And this is million times less than that, but we have to keep it because it has temperature. This is the only one that will contribute to thermal capacitance. Now we return back. We said G is equal to, we return back to electrons or to neutrons. Two most important examples of using of these formulas are the electron gas and the metals, electron hole for that matter, carriers in the metals, or it is neutrons in a neutron star. We just substitute mu, just open up this parenthesis, we get this simple expression. It's just simple arithmetic. Nothing done, just open up parenthesis. And again, this is my parameter. It is on order of typical 10 to minus 6. Maybe 10 to minus 4 at highest temperatures. You can think about. So this omega is sum of two terms. First term does depend on temperature. So this is grand canonical potential of completely degenerate electron gas, taking a temperature equals 0. And this is a very small term. It's about 6 orders less than this first one, but it does depend on temperature. It's leading correction in temperature. And the fact that this term is so small tells you that in the future, when we compute, thermal capacitance will be much smaller than you would expect for the classical ideal gas. And that is the case, and therefore it was called degenerate. Because at the time, all the theory, of course, didn't exist when thermal capacitance was measured. And no one can tell, no, this degeneracy doesn't exist. Now we'll find thermal properties. We'll start with entropy. So entropy is a derivative of grand canonical potential over temperature. We fixed at fixed V and mu. So there was square of potential, square of temperature, so it simply adds coefficient of 2. And 1 power less of t, first power of t. Now, comes important point. To find Cp or Cv, we have to express entropy in terms of n instead of mu. And the reason is that Cv, say, is a derivative of t multiplied by the derivative of s over dt at a constant n and v, not a constant mu and v. But we have an expression for s, and we can simply substitute mu in terms of number of particles. To do so, we'll calculate n of mu, which we have it actually. We calculated it already. We'll reverse it, find mu of n, substitute it here, and S is already first power and small parameter. It contains temperature. Then n of mu is sufficient to calculate in 0 order only, because if you include next order, the correction will be third order. It will contain TQ, and we don't take these terms into account. So it's enough to calculate n in the lowest order when n will be minus d omega naught. D omega naught value 0 temperature over d mu, the constant T and V, and we had this expression trivially differentiate was mu to the power of 5 half, now at power of 3 half. We can resolve it with respect to mu. So to resolve this expression, find mu of this, raise everything to power of 3 half, multiply by 3 pi squared h cube, divide by v. This is what we have. Raised to the power of 2/3. And then what is left? H cubed to the power of 2/3, which is h squared, divided by 2m. And this is actually expression that we already know. We got it before, at the very beginning, when we considered completely degenerate ideal electron gas. If we can obtain it different methods. But now we obtain it systematically from grand canonical potential, and it has exactly the same value as it must. Now we take mu and substitute it here. We get S in the. Thus we obtain expression for entropy in the variables we need, which is number of particles, volume, and temperature. So these are the variables of Helmholtz free energy. And from this expression, we immediately find Cv is T ds over dt at a constant V. So differentiation over T does not touch N, does not touch V. We differentiate here at T first power, simply disappears due to differentiation. Then we multiply back by T, so I restore it back. So we get back S. So in this approximation, Cv is equal to S. And here I write the expression, I repeat it. So this is not only S, but also is Cv. Just repeat it. And it has very characteristic behavior at the first power of T. And this can be compared to thermal capacitance, which is due to acoustical phonons in the Debye model, whereas Cv is T cube. And of course, the electron contribution decreases slower when T tends to 0. Only first power instead of third. So eventually it wins. And then at very low temperature, and we have at very low temperature, extremely low temperature, the conduction electric contribution wins at its Cv proportional to T. So what we see from solid is behavior at T cube for low but not very low temperature, and for extremely low temperature, if it is conductor, it remains conductor, the dependence on temperature changes and we get only first power of T. It decreases much, much slower. That said, I can make a comment that there are two things that can happen to conductor at a very low temperature. First of this conductor is actually an n-doped semiconductor, or any doped semiconductor. So for doped semiconductor, there is activation energy. This energy needed to ionize the dopant to give free carrier. When temperature becomes less than this activation energy, the dopant stopped activating, it is not ionized anymore, and free carriers disappear. So at this low temperature, instead of conductor, we got insulator. So then Cv will not be proportional to T, it will be still proportional to T cube, because phonon contribution still will be there. Another similar case with similar behavior is the case when conductor at very low temperature becomes superconductor. And it becomes superconductor, Cooper pairs formed, and there is a binding energy of a pair. And when temperature is less than binding energy of the pair cannot be broken. And such superconducting electron gas stopped reacting to temperature. It has exponential small CV, so leading term still will be dBi contribution T cube. So it changes. It changes from T to T cube, but X, so it initially T cube, then it is T at very low temperature, it's again T cube, because free electrons disappears. So life is not extremely simple, but not extremely complicated either. With this comment, I complete the statistical mechanics of an almost degenerate ideal Fermi gas. Next slide, a couple of slides. We have a bonus material. We'll show that in the limit of very low temperatures, always CV is equal CP. Next slide. Now this is the bonus material. I will show that for very low temperatures, always CV is equal to CP. To show it, we start with an identity that you know the exact thermodynamic identity. Cp minus Cv is Vt alpha squared divided by kappa at C. Here alpha is coefficient of Bell's expansion or expansivity. So it's derivative dv over dt at a constant p and n normalized to v. And we can express the same derivative using Maxwell relation for the Gibbs potential. Becomes ds over dp. As a dependence on T, let us assume that S has power dependence. It's always at low temperature. It's either power dependence or it's exponentially small. So we assume it's power dependence, where n is some power, and in our case n is equal to 1. And for say the Debye model, n is equal to 3. Obviously, the same dependence has alpha, because alpha is ds over dp. It does not touch dependence on T. It's just a coefficient at S, at the rest of S. So alpha, it will be T to the power of n. In contrast, kappa T in this formula is 1 over dv over dp. And this derivative is finite even at 0 temperature. Because when I decrease V, P increases because energy of the system increases due to quantum confinement. So it is a quantum effect. And kappa is a constant when temperature becomes very small. So it's T naught. It scales as T naught. So consequently, Cp minus Cv behaves as this is 2n plus 1 T to the power of 2n plus 1. It is much higher than dependence of Cv itself, T to the n. So this tends to 0 much faster than Cv. So in this approximation, Cp is equal to Cv. This always will be the case at very low temperatures. Our lecture came to an end.